The distance between us and Proxima Centauri, the nearest star to Earth, is 266,000 times higher than the distance between us and the Sun, and 103 million times greater than the distance between us and the Moon. Isn't it amazing? Even a ray of light traveling at the highest speed permitted by physical laws takes 4.3 years to reach us from Proxima, but less than 8.5 minutes are required to fill the space between us and the Sun. Hello and welcome to Zeey. In this video, we try to see if humanity will ever travel among stars. The difficulty of interplanetary travel is contained within these numbers and their relentless inevitability. When we consider the size of our galaxy, which is approximately 100.000 light-years in diameter, and the extent of the observable universe, more than 12 billion light-years, we are left with a profound sense of inadequacy. To appreciate our current technological limitations, consider that the Voyager 1 probe, currently the fastest interstellar object manufactured by man, is moving away from the Sun at a speed of 17 kilometers per second and will take approximately 75,000 years to reach Proxima. Traditional chemical fuel rockets, notwithstanding the gravity assist of Jupiter and Saturn, are clearly insufficient for such distances, necessitating a dramatic technical leap. Many proposals have been offered in this area, ranging from rockets driven by nuclear fission and fusion to those powered by matter-antimatter annihilation to massive sails propelled by light. These are simply theoretical ideas that would require decades of research and massive scientific and economic efforts to actualize. For the distant future, and all to be verified, some have proposed the use of warp engines that exist only in our dreams, or wormholes, fanciful solutions that start from the hypothesis of general relativity taken to its logical conclusion, and that could ensure movements at speeds faster than light. But it isn't merely a matter of creating bigger, better, and faster spaceships, or of waiting for science and technology to take their course. As we will see in a moment, there is a physical impossibility that slows, if not stops, our ideas for free and speedy navigation in the galaxy. It would be necessary to greatly raise the speed for interplanetary travel to become appealing to humans and to activate that combination of aspiration, ambition, curiosity, and competition that fuels our greatest undertakings. But this is simply not practicable for a variety of reasons. The implied findings of the renowned Fermi paradox also indicate this impossible. No object with mass can outrun the speed of light, as Albert Einstein demonstrated in his special theory of relativity in 1905. Einstein established this limit based on considerations that seemed, and still seem, to contradict the common sense with which we are accustomed to evaluating physical phenomena in our daily lives, but this does not change the fact that the limit has been verified in numerous experiments, and that there is no reason to doubt the existence of matter and the universe. In fact, Einstein established that the energy E of every object is proportional to its mass m using the famous equation E equals mc squared, where c is the speed of light in vacuum, which is 299.792 for 58 km per second. This relationship implies, among other things, that energy and mass are two equivalent entities that can be transformed into one another. And this is exactly what happens when we accelerate an object. The energy we give it goes to increase its mass in a very little part. However, when the speed grows, we require more and more energy to maintain the speed, which occurs because more and more energy is converted into mass. In practice, the closer an object gets to the speed of light, the more enormous and immovable it becomes. For example, if it traveled at 99.9% the speed of light, an 80 kilograms individual would have a mass of nearly 2 tons. To try to supply more push to the object or spaceship in order to cross the barrier of 300.000 kilometers per second would have merely resulted in an exponential increase in its mass, leaving the speed almost unchanged. As a result, speed c can be approximated but never attained. In short, bodies with mass are resistant to being accelerated to speeds similar to those of light, and the closer you go to this speed, the more difficult it is to accelerate them further. Even if you could instantly travel at the speed of light with a magical technology, it would still take 4.3 years to reach Proxima Centauri. This means that even at the fastest speed possible in our universe, our race could only complete a few rounds of exploration around the sun, but could never construct a network of trade routes across the entire galaxy. Of course, mass isn't the only variable that changes with speed. Time dilation is another aspect to consider when traveling through space at relativistic speeds. Time does not move uniformly for all witnesses, contrary to what classical physics postulates, but the slower the observer who measures a certain event approaches the speed of light. Leaving aside the physical and mathematical explanations, we must believe the truth unequivocally proven that on board a starship leaving the Earth at relativistic speeds, time always passes slower than on the planet it has just left. Consider a spacecraft traveling at 95% the speed of light to a planet 9.5 light-years away. A stationary observer on Earth would calculate the voyage time by dividing the distance by the speed, or 9.5 divided by 0.95 is equal to 10 years. The spaceship crew, on the other hand, experiences time dilation and perceives the journey to take only 3.12 years. In other words, the crew members aged somewhat more than 3 years between leaving Earth and arriving at their destination, whereas humans on Earth aged 10 years. And this time lag is caused by a relatively simple formula, which can predict, for example, that if a spaceship speeds up to 50% of c, time will appear to pass 1.15 times slower for its crew than it does on Earth, while at 75% of c, it will appear to pass 1.5 times slower. Time on board will flow 7 times slower if the speed hits 99% of c. And at 99.99% of c, time will flow 70 times slower, and if the speed reaches 99.9999999% of c, time will flow 22,300 times slower on board the spaceship until it appears to stop altogether at 100% of c. These figures, which could lead to some optimism about the possibility of moving it throughout the galaxy, reveal something startling. They tell us that for an observer moving at around 100% of the speed of light, his journey to any destination, whether 100 light-years or 100,000 light-years away, will be practically instantaneous. Do you still not believe it? Here's an illustrative example. We want to go from Earth to the Andromeda Galaxy, which is approximately 2.5 million light-years away. The trip would obviously last roughly 2.5 million years if it was completed with an acceleration capable of delivering the ship at a speed equal to 99.99% of c. However, on board the ship, the perceived duration is only 35,000 years. Not only that, but by increasing the speed by nothing, only 30 kilometers per second, it would achieve 99.9999999% of the speed of light, allowing it to reach Andromeda in just over 11 years. Isn't it amazing? If it were truly possible, we could reach the much-touted Star Trek scenario in which spaceships travel effortlessly from one place to another in the galaxy. So, does time dilation resolve the issue? Unfortunately not. As previously demonstrated, accelerating a mass to the speed of light would eventually need nearly unlimited energy. No known source of propulsion could provide us with this gift. Even if the energy problem is handled in ways that we cannot predict, a spaceship moving at close to the speed of light would be in a very dangerous situation. Space is not, in fact, empty. On the contrary, it is full of stray atoms that occasionally combine to form more complex forms such as gas and dust of interstellar clouds, galaxies, stars, and planets, while at other times remain only lonely atoms traveling to nowhere and unlikely to collide with another atom for thousands of years. The likelihood of a collision between two hydrogen atoms in a cubic centimeter of space is one thing. The certainty of a massive stream of particles colliding with the spacecraft during its journey is another. Particles are almost harmless at low speeds, but as they accelerate, they turn into a lethal shower of projectiles and ionizing radiation with great penetrating power, capable of gravely damaging the hull and making the occupants dangerously radioactive. The particles, intercepted at near to the speed of light, would gain enough energy to be lethal to any kind of life on board, not to mention that at that speed, it could be enough to cross a thin nebular veil and destroy the ship completely. Some scientists believe that interstellar matter alone will be sufficient to prevent a starship from reaching speeds faster than 1/10 the speed of light, which, as we have shown, are much too slow to maintain a network of large-scale trade and exploration routes. Even if all of these challenges were addressed, another insurmountable difficulty would remain. Time dilation would effectively cut all bridges between the traveling starship and the planet of origin. The astronauts would leave with the knowledge that they would never see their families, relatives, or friends again unless they did not bring them with them or did not have them at all on their return. However, they would find a society vastly different from the one they left. Not only that, but such a mode of travel would preclude the existence of interstellar institutions such as the United Federation of Planets, which are based solely on trade and cultural exchanges between different races and assume a homogeneous level of technological and social progress, homogeneity that is incompatible with the time required for such interstellar travel. In fact, what might compel a future commercial firm to transport its goods to the other side of the galaxy, knowing that it will never see or contact with the spaceship to which it has committed its cargo? Every spaceship that journeys beyond the realm of Einsteinian relativity will become a world unto itself, with no homeland and no past. What is the point of that? In actuality, this is a situation that will never come to pass. This is what Enrico Fermi tells us through the logic of his famous conundrum. If extraterrestrials exist, why aren't they already here? Wondered the Italian physicist. A simple thought can provide a solution to the following question. The universe as we know it has been around for approximately 13 billion years, and based on what occurred to our species, it takes 5 billion years for a planet of a solar-type star to develop sentient life. This suggests that millions of civilizations existed before ours, and they had millennia to create technology capable of taking them to space. Their absence demonstrates that traveling between stars at the speed of light is a feat beyond the capabilities of any civilization, and thus, the answer to Fermi is this: if they are not here, it does not mean that extraterrestrials do not exist, but simply that physics does not provide solutions capable of canceling distances, neither warp engines nor space-time tunnels. We, like all the other occupants of the galaxy, shall be obliged to remain forever imprisoned in the garden of the house, content with some laborious exploratory wanderings towards the 2 or 3 nearest stars. Alright everyone, here's where the video ends. Thanks for watching. Tell us what do you think in the comments, and don't forget to subscribe.